Okay, so good morning. Welcome to April Fool's Day. Uh, May GEO 319 lecture on April 1st. So, well, the first thing I wanted to do is ask if anybody was in Missoula and felt the earthquake yesterday.
Yeah.
What? Nope. No one?
I did.
I'm in Boise and I felt it.
Oh, I bet you did. Yeah.
Yeah.
I'm in Missoula and I didn't feel it, but my brother was in the basement of our house and he did.
Yeah, I was the only one in my house that felt it. I was yelling at everybody, but they were like tuned out. They didn't even notice that their whole house was shaking. So we're going to talk about biogeochemical cycling today, but I did want to take a little detour just because it's not every day you have a magnitude 6.5 earthquake that you get to feel. And so I wanted to show you guys a little bit of the data and the places to go to check this out. So I'm going to go to USGS earthquakes. All right, so first of all, I felt the earthquake and I went straight to the USGS website, and within 5 minutes they had the magnitude and pretty close to the right location up. So if that, I had a whole bunch of friends who know I'm work in the Department of Geology, so they assume I'm an expert on earthquakes, texting me after it happened. And it was really easy to know what happened just by going to the USGS website. So you can go to this list of latest earthquakes. And right here is our well, first of all, let's just look at these guys. So here's the magnitude 6.5 just west of Chalice. All right, so this was the big one. And then what you can see is all of there's a whole bunch of aftershocks that occur after this guy. So it's pretty interesting just to watch all the seismicity. All right, so here's the Chalice, the big one. You can click on it and it'll pull up a whole web page of information about the earthquake. So if you're curious or if you have friends who are asking you about it, this web page is full of all kinds of great information. One of the coolest maps that I saw. So here, this is the USGS interactive map, and these contours are their computer modeled intensity of shaking. So you can see here's the epicenter, intensity of shaking, moving radially out from the earthquake. One of my favorite maps was the community intensity map. So this is the intensity map of people reporting what they felt. So this is like real citizen science. It's just, you can actually report what you felt. Your felt report, put it in here. You tell where you're at, what you actually felt, and then you'll get put into this map, and it'll record basically where people felt things and what they felt. And I think it's really cool to look at. It's pretty darn accurate. Like what people felt is much, stronger around the epicenter, and you can see, sort of how far out people were feeling things, and how light they were or strong. So at any rate, it'll tell you all kinds of cool stuff about the earthquake. One of my friends asked me, well, do you think there'll be any new rapids on the Salmon River? And so, well, right here, ground failure limited to right around the epicenter. And so, pretty confident that there's not going to be any new rapids on the Salmon, but you never know. There might be one or two small ones.
Something else that's interesting is that epicenter is located right where there was like a 4,000 or 5,000 acre fire this last year. So I was curious, like, what effects it might have on some of those dead trees.
Yeah, right. If there was a fire this year, I don't know. I guess some of the roots could have got burnt out. I would guess most of them still have their roots mostly intact. I don't know about the fire itself, but yeah, we could have had knocked down a bunch of trees. So let's see what else is cool on this map. So the moment tensor, this is you can get really lost in learning how to read these beach balls, but this tells us what kind of fault it was. And the bottom line is when you've got a sort of band of white in the middle and dark on either side, it's usually a normal fault. So this was a normal fault. That means it occurred under extension. It's a little bit of a mixed fault because there's some strike slip component to it. So a strike slip would look like a checkerboard. So it was a normal fault that moved a little bit obliquely. So big extensional fault, pretty interesting. The location, where it is. So if we go back, actually, I'm going to pull up a map of seismicity in the area here. So let's go here. I'm going to go 30 days, magnitude 2.5. Past 30 days, magnitude 2.5, US. Search. What? Huh. For some reason, probably because everybody in the world's searching this right now. I'm not able to pull up all the earthquakes I want to pull up. What's this guy? What I wanted to do is look at the regional seismicity around here and just show you guys. Let's see if it'll work now. 30 days, magnitude 2.5. No, it's not working. Let's go here. So one of the things, just when we look at this map, this is the Snake River Plain. Here is Yellowstone National Park. And there's a whole bunch of seismicity or earthquakes around Yellowstone, just a ton. And all along these flanks of the Snake River Plain. So this earthquake has some sort of, you know, relationship to the Snake River Plain and Yellowstone seismicity, but it's pretty distal. It's way up north here in the mountains. And so I was talking with Rebecca Bendick a little bit about why there might be an earthquake so far north away from the Snake River Plain. And she thought it was pretty interesting too. It's not a place I would have thought we would get a magnitude 6.5 earthquake. So pretty weird location actually, but probably related to this Yellowstone seismicity belt. There's a whole bunch of earthquakes that sort of follow they call it the bow wave around the Yellowstone hotspot here in the Snake River Plain. All right, I'm done talking about the earthquake unless people have any questions that I can try to answer. If the one of the things I wanted to do is just show you the actual MBMG. So the Montana Bureau of Mines and Geology. Let's go geohazards. And do not.
Dr. Gardner?
Yeah.
We can't see your screen, by the way.
Oh, you can't see my screen? That's hilarious. How long did you just let me do that? Jesus. Oh my gosh. Okay. Well, now you can see my screen. Yeah, next time you guys should definitely tell me that's happening. Can you see my screen now?
Yes.
All right. Right here, web recorders. We can look at the can see the Missoula, or I'm going to check out the Missoula seismic station. So Hillary Martins in our department has several seismometers around Missoula that are hooked up to the Montana Bureau of Mines and Geology and feed to that USGS site. So here is the web recorder from the 31st. And essentially each one of these lines, like this is the line at 4 o'clock or yesterday morning. All right, so you're looking at a timeline. This is 4 o'clock. This line is 5 o'clock, 6 o'clock. And so they just kind of keep going down in time. So here's 5 o'clock PM. All right, and we're going down, we're in black, green, blue, and then we're back to green. And then right here is where you can see the earthquake hit on the MSO recorder. So at this Montana Bureau of Mines site, you can look at all the waveforms from all over the state. So here's Dillon, for example. Here's a seismograph, a seismic station near Dillon. And here you can see the earthquake hit at the same time. So here's 5 o'clock. We're on that green band. This is, each one of these is 10 minutes. I think 15 minutes. So, you know, this is getting close to 6 o'clock, which is when the earthquake was, and you can see the earthquake hit. All right, and since I wasn't, oh, here's the seismicity pattern in Montana, maybe. It's not really giving me much. All right. This is the GeoHazards website for the Chalice, Idaho earthquake. This was what I was trying to tell you or show you guys when I was not sharing my screen. So all of these things, all of these, lots of cool data. You can look and learn about the earthquake if you're interested. All right, any other questions or comments about the earthquake? All right, if not, then we're going to get back to talking about biogeochemistry. And I asked you guys to read a paper on eutrophication. So I've got some reading questions that I will post on Moodle right now. So what I'm going to do, we're going to break out into discussion groups. I'm going to give you guys 15 minutes to discuss these questions and the paper. And then we'll come back. We'll talk about eutrophication and causes and consequences of eutrophication. So everybody should have a copy of the paper. It's under week 11. It's Carpenter 2008. I'm going to post a set of reading questions right now. All right, reading questions are up on the website, on Moodle. So I'm going to send you guys off into breakout rooms. Have we done this yet in this class? Okay, so here's how it works. I'm going to send you guys out into breakout rooms. Looks like there's 9 people today. So I'm going to do 3 breakout rooms. You get automatically assigned. It'll say you'll get I think you get sent an invitation to join the breakout room. You got to click join. And then you guys will be in your own little Zoom meeting. You talk, discuss. In 15 minutes, I'll bring you all back. All right. Look for little orange flashy things. If I have a message, I'll broadcast it to every breakout room as a chat, and it usually flashes orange on my Zoom software, at least the chat icon. All right, so I'm going to send you off into breakout rooms now. 15 minutes to discuss the paper. So I'll close the breakout rooms around 9:35, and I'll drop into each of your breakout rooms as you guys are discussing. All right, I'll see you in a bit. Okay, so you should be getting invitations. There we go. People are leaving, joining. Again. All right, so the algae, while they're growing, they're producing a ton of oxygen, and actually we can get really super saturated oxygen in our waters. But then the algae eventually start to die. They have limited time spans. And we've added all this organic carbon to our system. So what happens to the organic carbon when it falls to the bottom of our stream or our lake?
Well, the water provides an anoxious environment. So then you have the like the is it cyanobacteria?
Well,
Anyway, the anaerobes start multiplying exponentially. They start breaking down this um, the carbon, the organic
yeah.
carbon.
In fact, before even the anaerobes get started, that organic carbon starts to decay. That process, decay or respiration, does that produce or consume oxygen?
It consumes the oxygen.
Okay, respiration consumes the oxygen. All right. And so the oxygen in our water column gets used up. Now, once it's gone, things become anaerobic. Anaerobic means no oxygen. And then we get cyanobacteria, which are anaerobic bacteria, meaning they don't need oxygen to undergo respiration. They can breathe things like nitrate, hydrogen sulfide, and even produce methane. All right. So anaerobic bacteria can now undergo respiration using other things than oxygen, such as nitrate, ammonia. They can use ammonia. They can use all kinds of things. So bottom line is the nutrients add a bunch of organic carbon. That organic carbon decays, and we create these huge dead zones where there's no oxygen, and we get toxic cyanobacteria. Our water smells really bad, and it's really unhealthy. So that's eutrophication. All right, so what was causing the eutrophication? Well, we said it was the addition in this paper of nitrogen and phosphorus. Okay, so how do marine environments differ from the freshwater systems? What was the main difference there?
It was really big, so it's kind of hard to control it because there's a lot of systems, like the output of the river, like wash away.
Yeah, so it potentially is a much bigger system. What else about there was something about which nutrient was limiting?
The nitrogen, I think, was the limiting. Do I
Yeah,
have it backwards?
no, I think you're right. So we can go back, but I believe in the so in nitrogen is the key controlling factor for estuaries and oceans, while phosphorus appears to be the key one in freshwaters. So they have sort of different sensitivities to different nutrients.
Wouldn't the estuaries also have a higher turnover rate, so you would have a less chance of eutrophication?
That's not necessarily true. No, it's that's solely a function of inputs. In fact, how did we talked about the equation to determine sort of residence time in a reservoir or turnover rate? You guys remember what that was? It is, let's see, let me share my screen. The bottom line is the residence time. So tau, the residence time, was equal to the volume of our reservoir divided by the inputs, or the discharge in or out. All right.
Okay.
So it is completely dependent upon the volume of the lake, river, or estuary, or the ratio of the volume to the inputs. All right. So in an estuary, some of them are huge and they have very low turnover times. And some lakes, like Flathead Lake, has an extremely fast turnover time. So it just depends. It's not, you can't really make that statement. But what is the right statement is that it would depend on the turnover time, how sensitive you are to eutrophication is dependent upon turnover time of your system. Okay, so what were some activities that we could do to control nitrogen and phosphorus in the aquatic system?
Decrease consumption in meat,
Okay.
because then they would decrease the amount of fertilizer.
Yeah, it decreases the amount of manure. And manure, so one thing that's interesting is you tend to think of organic farming as being better, all right? But manure is generally what we fertilize with in organic farming, and manure is really high in phosphorus. And so for eutrophication, it might be actually worse. So it's an interesting thing to think about there. Yeah, so we could change how much fertilizers we're using, what kinds of fertilizers we're using. What we're going to talk about Friday are other changes, and that is, how does the nitrogen and phosphorus get from the land to the stream, and how can we think about changes we could make in those transport mechanisms. All right, we're out of time, so I put a place to turn these in up on Moodle. So turn your answers to these questions in on Moodle. If you can, save it as a PDF before you turn it in, because then it makes it easier for me to grade. I don't have to download the file. I can just look at it on Moodle if it's a PDF. If it's a Word document, I have to download it to look at it. So save it as a PDF and then turn it in on Moodle to get credit for this class activity. Friday, we're going to talk about transport mechanisms and how we might expect systems to respond and react to changes in the nutrient cycles. All right, any business questions before we go today? All right, hope you guys had a good day and have a good rest of your day, and I'll see you on Friday.